Hi! In this presentation, we will be summarizing the main features of our project, FriendlyEyes, designed by electrical engineering majors Manuel Nunez, Victor Lopez, and Michelle Dubon, as well as computer engineering major Joseph Brown. FriendlyEyes is an electromechanical system designed to emulate the role of human vision in scanning our surroundings while walking, aimed to offer an alternative to the white cane while providing wider functionality. This project came to be because of the fact that there's an estimated 40 million blind people worldwide, along with approximately 300 million more experiencing moderate to severe visual impairment. The classic white cane has been effectively used as a navigation aid for years, but while overall global technological development has been rampant, no technology has had major breakthroughs for this particular necessity. Products like Ultra Cane and Ultrasonic Cane and Iron Man, a wearable retrofitted with sensors that acts as a navigational tool, show promise, but all of these fail to account for what we define to be the main three functions our vision performs while we move around a space. One, the ability to define where an object is located as well as how far it is. Two, the ability to engage a state of alert when something is coming our way. And three, the ability to spot the possibility of falling because of terrain changes. Having these key issues in mind, our required specifications for FriendlyEyes were that FriendlyEyes must be able to scan the user's field of view up to 7 meters away and use it to produce a mechanical output that will work as a navigation assistance. FriendlyEyes must issue and prioritize alerts prompted by objects coming into 10 meters from the user and doing so with speeds faster than 2 meters per second relative to the Earth, which would be higher than the average walking speed of 1.4 meters per second. FriendlyEyes must keep track of its distance from the ground and alert the user of sudden changes in the level of the terrain ahead of an incident. FriendlyEyes must produce all alerts within 1/8 seconds of sensing to provide the user with enough time to make informed decisions on next steps. FriendlyEyes must be powered by a rechargeable battery and the system must run for at least 8 hours on a single charge. FriendlyEyes must be safe for anyone who wears it, therefore, it must be able to assess known and common dangerous materials such as glass, keep temperatures low all around the system, handle electrostatic discharge, risk appropriately, and most importantly, be widely tested.
In order to meet these requirements, we thought of implementing an electromechanical system housed within a piece of clothing that, in its simplest form, would take input from sensors, perform its calculations and comparisons, and subsequently output a localized vibration, all powered from a rechargeable battery. For the purpose of keeping processing and power requirements at a minimum, at the heart of our system would lie an algorithm relying on the widely popular and efficient fast Fourier transform, using it as a tool to obtain a real-time representation of how close things are relative to the user from simple power spectral density calculations. Then, appropriate thresholds can be set for a computer to perform the comparisons and carry out a response. This simplified block diagram shows a generalized picture of the functionality of FriendlyEyes, but we will take a more detailed look after all subsystems have been presented. The first step in developing our project was to find wireless sensing technologies that would enable our application. The main points of concern during this investigation were based around the physics of its working mechanism, on which I'll expand in a second, it having digital communication methods for higher reliability on the handling of data, as well as more levels of freedom to work with while developing our application. The price tag, since we are aiming to make an accessible product, and tied to that, the availability of components is something to be wary of these days. Power requirements, since we'd need the system to run for 8 hours or more, and finally, it being and they being compatible amongst themselves. That's the different sensor modules that we're gonna use, and I'll expand on that in a second also. From this investigation of wireless technologies, we discarded the use of those operating with wavelengths in the order of the micrometers and below, since there were no off-the-shelf products that could carry out the measurements we need for our algorithm without demanding more from our power or processing budgets or having a higher price tag than the project finances allowed. Um, we found our solution in the realm of the millimeter waves with Aconir's A1 pulse coherent radar sensor IC. The company developed and patented the pulse coherent radar method of sensing, and what it does basically is it turns off the transmitter in between pulses, which will in turn, of course, lower power consumption. But what PCR does is, other than that, is it allows for more flexibility for developers, since parameters like the pulse duration can be tuned to fit the needs of a wide range of signal processing applications. The chip itself carries built-in folded dipole antennas operating at 60 gigahertz, and it also has an internal program memory and internal data memory. All these easily accessible through an SPI interface, I should say. Lastly, and maybe most importantly, its elevation and azimuth angle form a tall and wide cloud-like capture area, which is essential for the creation of the 3D array of power spectral information we are looking to create. Then, to cover our second area of concern, we favor the pre-built module since it will ensure its task will be carried out as intended, with its task being one of high priority because of its implications for user safety. We went with Innocent's INS 3330. It's a Doppler radar sensor module. It has integrated DSP and UART communications interface. It's radar but operates in the 24 gigahertz band, so no clashes, and it can deliver raw envelope data or pre-process this data and deliver information on the velocity of objects entering its umbrella of coverage in the form of vectors. Finally, we looked for a cheap and effective way of implementing a depth tracking feature. We went for a set of two ultrasonic sensors for this purpose. The sensors would be placed at an angle so that they look ahead of the user and to the opposite direction of each other. For them to work as intended, the system must offer a standard calibration process to account for differences in different users' height. So, summarizing, the sensor subsystem for FriendlyEyes will consist of three different technologies working together to guide its users' navigation. The system will have an image formed on which to rely on for calculations covering the range comprehended between 0.3 and 6 meters. The system will be in the lookout for moving threads coming the user's way up to 9 meters away, and the system will also constantly monitor the level of the ground, ensuring smooth walks for the visually impaired.
Our original microcontroller considerations were primarily Texas Instruments boards that we had experience with in our curriculum, from classes such as embedded systems. However, for this project, we specifically wanted to use an ARM processor. Partially for the learning experience, ARM devices are popular in industry, but also because of recommendations given by Aconir, the manufacturer of the A1 radar sensor we are using. Among the ARM microcontrollers we were considering, Maxim Integrated's MAX32625 pulled ahead after worries arose due to the low memory available in other devices, as well as their comparatively low clock speed. The wealth of available interfaces was another factor that pushed us in this direction. At the moment, we are using one UART for the INS3330, one SPI for the A1, and our two ultrasonic sensors will use one wire. However, flex schools would require an additional I2C interface. The 10-bit ADC is as accurate as needed, since we are only capable of relaying so much information to the user via the few vibration motors being used, so the extra bits of precision offered in other microcontrollers was not necessary. The development board for the MAX32625 was also much better than many of the competitors' offerings. The MAX32625 Pico is the development board for the MAX32625. It is a relatively cheap development kit, coming in at just over $10. Programming the board is extremely easy. Compiled bin files are simply drag and dropped onto the board via USB after setting the board to its proper mode. The device is also capable of being used as a programmer for the microcontroller itself. After being set to the proper mode and having the SWD cable connected, again just drag and drop your compiled bin file onto the board and all flashing will be done for you. Writing programs for the board is also made much easier due to its compatibility with the Mbed SDK. Here, hardware is abstracted, making it much more intuitive to write nice and concise code. This abstraction also means that code written for one device may work on another with minimum changes required. There are also a huge number of public repositories available right on their website, allowing one to find example code for effectively any problem that they may encounter.
We're going to be taking a closer look at our power schematic. The first set of voltage regulators are the ones supplying power to our microcontroller. We are using 3 different power circuits to supply our microcontroller with 3 different voltage levels. The NCP115 has a 1.8 volt output voltage and a 300 milliamp maximum output current. It has a 1.7 volt to 5.5 volt input voltage range. The MIC5205 has a 3.3 volt output voltage and a 150 milliamp maximum output current. It has a 2.2 volt to 16 volt input voltage range. The MIC5258 has a 1.2 volt output voltage and a 150 milliamp maximum output current. The 3 power rails are not being shared with any other device and serve the exclusive purpose of powering the 3 voltage supply pins of the microcontroller. There are 2 different power circuits being used for the A111 radar sensor. The first is the ST1S1, which we are using for power conditioning of the A111. Power conditioning is important because it protects sensitive loads to devices by smoothing out voltage fluctuations. The ST1S1 has a selectable fixed output voltage of 1.2 volts or 1.8 volts and a 700 milliamp maximum output current. It has a 2.5 volt to 5.5 volt input voltage range. The second is the SIP3243, which we are using to supply power to the A111 radar sensor. The SIP3243 is a high enable logic load switch, and we have it configured to produce 1.8 volts. It has a 1400 milliamp maximum output current and a 1.5 volt to 5.5 volt input voltage range. We chose a load switch to power the A111 sensor because they safely minimize power consumption, which is important for the consideration of the longevity of the battery. The ISL 9111 voltage regulator will be used to supply power to the INS 3330 radar sensor and the URM09 ultrasonic sensor. The ISL 9111 has a 5 volt output voltage and a 800 milliamp output current. It has a 0.5 volt to 4.8 volt input voltage range. Additionally, we needed a voltage regulator that would take power supplied from a COTS, a commercial off-the-shelf AC adapter, and convert it to power usable by our system. The MP2018 has a selectable fixed output current of 3.3 volts or 5 volts and a 500 milliamp maximum output current. It has a 3.3 volt to 16 volt voltage range. The MEP 2018 will be used for battery charging and stability. Determining the maximum current draw and voltage of each device was important to us because we needed to understand what the possible power consumption of our device would look like. With these calculations, we could determine what the battery size would be. We chose the worst case scenario where all the sensors and microcontroller would be drawing their maximum current draw. The actual power consumption by the sensors and all the other components going into our device will be lower. The designs of the voltage regulators were chosen using the Texas Instruments WeBench Power Designer and modified slightly to fit our device's design.
When selecting the batteries, there are many types of chemical combinations in the market with different characteristics. Lithium-ion batteries is the most popular type of battery in the world due to its high energy density. They do not show memory effect, low self-discharge rate, and they are relatively low cost. However, these batteries are not robust as other batteries. Lithium polymers have the same characteristic as lithium-ion, but they have a higher energy density. This means that they can have the same amount of watt-hour but with less weight. The only difference is that they are more expensive than lithium ion, and due to its chemical combination, extra security tests need to be considered. After doing more research and testing the batteries, we came to the conclusion that the best option was the lithium ion or lithium polymer, because they have a nominal voltage value of 3.7 volts and a life around 3 to 5 years. The main difference is the chemical combination. The lithium polymer has more energy density, meaning that it weighs less than the lithium ion, and also it is more robust and safer for the user. For that reason, the lithium polymer is the battery that we choose to do more testing and to use in the final version of the project. The battery is always going to be close to the user, almost in contact with the skin of the person. For that reason, the battery needs to be small and lightweight. Those characteristics are the main advantage of the lithium batteries. The lithium polymer battery that we choose weighs 150 grams and it can provide 22.2 watts-hour. Also, they have already some security systems integrated to avoid any problem. The battery will be attached to the base next to the power PCB that provides power to all the components in the project. To charge the battery, we are going to use a AC-DC from Amazon that converts 120 AC bulbs to 12 bulbs DC with a maximum of 6 amp of current. After, that is connected to a DC-DC that steps it down to 4.2 volts and a voltage regulator that keeps the voltage constant in case of any increase or decrease from the grid. After, the voltage regulator connects to a MOSFET that once the voltage of the battery is fully charged, it disconnects the battery from the charging station to avoid overcharge. Nowadays, many of the voltage regulators have overcurrent, overvoltage, and short circuit protection included that make the battery safer than before without adding more ICs or components. Because the battery is going to be almost in touch with the user, avoid any possible harm is crucial for a project, and making a redundant system is part of the solution.
Here we can see a comprehensive block diagram of the system. To test and successfully integrate a removing piece of this system, we took a phased approach and developed a number of PCBs, each carrying one or two of the main components FriendlyEyes will be using. These allowed us to delegate tasks more efficiently and to avoid overloading ourselves by leaving too many possibilities for failure open. From this process, we have run into issues such as the cost of having multiple communication protocols sharing one board, component placement for improved SNR, considerations to minimize distortion and crosstalk, finding a proper PCB stack-up, and the list goes on. Up until now, though, the leading idea for the implementation of the whole system relies on modularity as a means to limit the level of the noise floor as much as possible, and also to reach the aforementioned most optimal physical placement in the garment. This setup isolates the MCU and A1 sensor from the noise caused by the 5-volt boost regulator's switching frequency, which we know to be problematic, and keeps SPI transmission lines short and protected within their own board. The decision to carry a phased design approach for the hardware presented us with many of the possible pitfalls we could have found on our way earlier during development, and having thought of premeditated debugging method, so we consider most of our hardware development to be close to completion.
Up until now, we have early confirmation that our chosen battery meets the requirement of powering the system for a minimum of 8 hours from breadboard tests we performed, but at the moment we are setting up the environment to run a proper battery characterization process and obtain data to back this claim. We will be running charge and discharge tests on a random selection of battery from our stock, tracking the actual charge of the battery using a dedicated IC, while current is drawn from the battery by loads simulating scenarios of interest.
The problems we are currently facing relate more to the application and adaptation of our system in a real-world setting. Some of these problems are trade-offs in digital signal processing, such as resolution versus cost. This is evident when we consider that for this mechanism to work, all quantities used in calculations are relative to the user's position or speed, and also when considering that the simple act of walking requires us to move up and down, and these small movements can throw off measurements when the beam is being generated from such a small source. Another real-world caveat that we must work around is that of finding the most optimal location to place the main enclosure in the garment, as well as the vibrational motors and necessary wiring. For our final steps, we will need to integrate all these subsystems into the same PCB, as well as make improvements in expanding and expediting the testing process. It would prove to be a major challenge to try and carry out all necessary testing such a product would need to go through in the short amount of time allocated to developing this project. In order to tackle the issues we are facing regarding digital signal processing, we are devising tests that will allow us to properly characterize our subsystem signal-to-noise ratio. Relating to this matter, we also acquired radar lenses that we'll be characterizing should it become necessary to improve this value for better results. Our immediate next steps will be based almost entirely around the integration process, starting by looking into electrostatic discharge considerations and working to include it in our final PCB. A few weeks from now, when the board is received and assembled, we will need to carry out extensive testing for our final PCB and the software that integrates the battery, sensors, and other subsystems together. If our results are positive, we will then proceed in attempting to reach our most desired stretch goal, implementing an SOS function to the system.
At the end of Senior Design 1, we came up with a budget of $372 to be used in the development of FriendlyEyes. The truth is that when we estimate that number, we were still missing information on the ins and outs of the financial side of engineering. The monetary cost of building a single FriendlyEyes unit is indeed much smaller than $372, coming in at about $115 and $130. Nonetheless, the cost of developing a project of such magnitude with so little experience requires us to branch past the budget cap we had set, and up until now we have spent around $500 with an expensive financial investment of around $700.
And with that, we conclude our presentation. Thank you very much.